This question has a lot going on. Let's just make a start. We've got the volume of this ornament is 2100 pi, and we're asked to get the value of capital R in terms of little r. In fact, let me just bring this down so I can keep my eye on it as I'm deriving. Okay, so let's deal with this in two parts. First of all, the hemisphere. The volume of the hemisphere is, well, the sphere, as we saw above, was 4/3 pi r cubed. So for a hemisphere, it's going to be half that, 2/3 pi r cubed. So in this case, the radius is capital R. So 2/3 pi r cubed like that. Then we've got the part of a cone, which is actually also called a frustum. So if we imagine extending the cone up to the top, this is going to be useful because we've got that the volume is 1/3 pi r squared h, but that is for a cone. So we basically need to take the large cone and subtract the small cone. Okay, so large cone, we've got 2r here, and then got to try and work out what the height would actually be, which we don't have at the moment, but we've got the small cone as well, and this has got a radius of r. So we can actually use the idea of similar triangles here. I've got a triangle with base 2r, and here I've got a triangle with base r. So it must be that going this way, I'm dividing by 2 for the lengths, and going this way, I'm timesing by 2. Okay, now I still don't actually have the height of either, but if I say that the height of the small one, no, the large one is h, then the small one would be h over 2. And now I can use that. I can say that, okay, that means that the bit left over when I subtract them is also h over 2, and I can see that's equal to 4r. And therefore h is 8r all along. Brilliant. And therefore the volume is 1/3 pi r squared, which just remember is actually 2r squared, times h, which we've just said is 8r. That's for the large cone. And I need to minus 1/3 times pi r squared this time for the small cone, times by h over 2, which is going to be, remember the height, h over 2 was 4r, so I'm actually timesing by 4r. Oh, okay, that one was quite involved. So I'm going to get 4 times 8, 32 over 3 pi r cubed minus 4 over 3 pi r cubed, which becomes 28 over 3 pi r cubed. Right, and remember that was 2100 pi in total, so therefore 2/3 pi capital R cubed plus 28 over 3 pi r cubed, different r's, is equal to 2100 pi. Divide through by pi, times through by 3, and then divide through by 2. Giving us a final answer, and I've lost it, but here it was. R cubed equals 3150 minus 14 r cubed. All right, even that bit is quite involved, but that is our starting point. Okay, on to the next part. We're asked to find an expression involving d capital R by d little r in terms of little r and or capital R. So the best way to do this is just go straight into implicit differentiation. If we differentiate the both sides with respect to little r, we'll get 3 capital R squared. Then using the chain rule, we then times by the derivative of capital R. And then this is simply going to equal minus 42 R squared. You could alternatively make capital R the subject by raising to the power of a third and then use a chain rule, but it's just going to get messy. And this is just such a simpler solution basically, because now we can divide through by 3 to take us back to 14. And we're going to get minus 14 little r squared over big R squared. And we're done. Then asked to find the visible surface area of the ornament. So I'm just going to borrow this diagram again. Okay, and we're going to figure it out bit by bit. So let me first of all focus on the hemisphere. I've got this curved part, and the whole surface area of a sphere is 4 pi r squared. So the curved part here is going to be 4 pi r squared over 2, or 2 pi capital R squared. And then we've got a flat bit at the bottom, which actually I might do this in a different color. So this bit here. So we're going to get pi r squared, but then I need to minus that small circle here. So minus pi r squared. That's where the truncated cone is touching the bottom of the hemisphere. Then this just leaves us the curved area of the truncated cone. But don't forget we had big cone with radius 2r, that's shown on the diagram, but we calculated that the height was actually 8r. And then I want to minus the curved area of this small cone at the top, which was 4r and r. So the formula is actually given right at the start. It's pi r L, in fact, where L is like the slanted height, but you can use Pythagoras' theorem to get root h squared plus r squared, and that's going to be more useful here. So pi r and then h squared plus r squared is going to be 8r squared plus 2r squared. Although I've just realized I've made a little mistake because there should be a 2 here. It should be pi times 2r, because I'm replacing all of my r's by 2r because that's what the radius is. And then I'm minusing pi times r for this smaller one times the height, 4r squared plus the radius squared, like that. All right, let's have a go at simplifying this. We're going to get 2 pi r and then root 64r squared plus 4r squared becomes 68r squared minus pi r, and then 16 plus 1 is 17, so 17r squared. Now root 68, actually 68 is 4 times 17, so we're going to get root 4 times root 17, or 2 root 17. So this becomes 4 pi r times another r times root 17. Because when I square root the r squared, I get back to r. So I've got my r squared, I've got a 2 because 68 became 2 root 17. That's that term. Then I'm minusing pi r squared root 17, which gives me 3 pi root 17 r squared. Oh, okay, we're there. So curved part of the hemisphere, flat part of the hemisphere, and then the curved part of the truncated cone. So the total observable surface area is 2 pi r squared. That was from the curved part of the hemisphere, plus pi capital R squared. That was from the flat part, but then we need to minus pi r squared there. And finally add 3 pi root 17 r squared on. Let's just make sure we write it in the correct way. We can just also check if we made a mistake, we can spot it. But I think this is all good. So we're going to get 3 root 17 minus 1. I can factorize out the pi r squared. And then add the other two terms together, leaving me 3 pi capital R squared overall. All right, nice job. Keep going. So in D, hence show that the derivative of the area is equal to that shown, but we have to find gamma and delta. So differentiating with respect to little r, I'm going to get the r squared goes to 2r, so I'm going to get 2 times 3 root 17 minus 1 pi r. And over here, when I differentiate capital R, I need to use the chain rule. So it will be go to 2 to d by dr of r squared is going to become 2 capital R and then the derivative. Essentially, I'm still using implicit differentiation. So I'm going to get 6 pi r times by d capital R over dr. And we want the whole, well, we want to get rid of this dr by dr. And earlier on, remember we showed that this is equal to minus 14 r squared over r squared. So I'll just tidy this up. I'm going to get 6 root 17 minus 2 pi r. So I think I've got myself sorted with gamma. And then I'm going to be doing minus 84 pi r squared over capital R squared. These are going to cancel and it all checks out. I'd be tempted actually just to, right, I'm just going to write one final. Right, that is now looking good. All right, that is A, B, C, and D completed. We've worked out we've used the volume to get a relationship between capital R and R. We have found an expression for d capital R by dr. We've investigated the area and then differentiated that as well. We move on to considering kind of moving away from the hemisphere and considering A as a function of little r and just what the graph looks like. This doesn't mean that it's going to be like there are going to be physical solutions at every point along it. So we've got a local minimum, that's r equals 0. We've got a local maximum, that's m, and an overall minimum point for the function for a at n, where the gradient's undefined because suddenly there's a kink in it. Okay, we're asked to work out the r coordinates of the point n. So actually that is going to be when the gradient is not defined. And so d capital R over dr The only time it's not defined is when the denominator is 0. So here, remember we've got a relationship between them. Uh, Lost where it was. Here we go. So here we're going to get that. Let me just borrow this. So at n, we're going to get that 14r cubed is equal to 3150. Then you can divide through. What should I do? Divide through by 7 first, maybe. 7's into 3150. Go 4, 5, 0. So 2r cubed is 450. Therefore, r cubed is 225. R is going to be the cube root of 225. E part 2, explain why the ornament little r must be less than this value, while we require, for the ornament to make any sense, that capital R is greater than 0. If it's equal to 0, then you're just going to get a truncated cone. It's not actually the original ornament, which implies that R must be less than the cube root of 225. So cannot have negative radius. I think in the answers they say like if it went beyond it, then capital R would become negative, which you can't have. But we also, for me, need to explain why it can't actually equal the value, because it says R has to be less than this value. So it can't equal the cube root of 225 either, because then the radius will be 0. This takes us to the very final part. We're asked to show the r coordinate of the point M is given by this, where we have to determine P and Q. So we've got the derivative in terms of little r and capital R. We've also got a relationship between capital R and little r. And at M, we know the stationary point will be 0. So what that means is that 6 root 17 minus 2 times pi r will equal 84 pi r squared all over capital R, which we can now rewrite as the cube root of that. Okay, we've got to solve this equation for little r. Now what we can immediately do is divide through by pi, divide through by r because we know that r is not 0, and there's a common factor of 2. So this becomes 3, this becomes 1, and this becomes 42. Okay, that makes it much easier. You might not spot that and have to do it later on. Because also bear in mind the answer, which I'm going to sort of bring along. Look, we can see we've got 3 root 17 minus 1, which I've managed to now get there. Okay, so next up I'm going to multiply, I'm going to basically rearrange it. So we've got the cube root of 3150 minus 14 r cubed, and that is going to equal 42. Or no, I want to multiply it by that third. Okay, And now I'm going to cube everything. Don't actually want to cube 42 if I can avoid it, so we'll just leave it like it is for the moment. And then need to expand this because I'm trying to solve for r. So 3150 times this. And then minus 14 r cubed times the same thing. That means that I can actually add them onto both sides, so that will equal this plus this, and I can now factorize out r cubed. Sorry, sometimes on my really long videos, I don't know, my computer stops being able to deal with all the writing and it gets a bit laggy and it just becomes a bit messy, so apologies. Okay, so I've taken out r cubed and then I've got, that was a plus, so I've got plus 42 cubed here. That means that r cubed is going to be okay, and we're very, very close, but you can see in the final answer there's no 14 here, so I need to divide through by 14. Well, 42 cubed is actually 42 times 42 squared, which is 3 times 14 times 42 squared. So if I divide through by 14, this will simply become 3 times 42 squared. And that's great because that is very similar to that. Then I just need to do 3,150 divided by 14, but earlier on we actually did that and got 225. So I'm there, really. I'm right at the end of my page, actually. I can't actually write anymore, so I'm just going to manage to just about fit this in. My final answer, 225, that is my value of p, times 3 root 17 minus 1 cubed all over. Okay, so well done on this. It's like a fairly ridiculous answer for the... Oh, sorry, I haven't actually cube rooted it. That is our final answer for this question. All right, like it. Good question. Well done.